Hello guys, my name is João Henrique da Rosa, and today I'm gonna present my paper, which it's about PAC-AI, a provenance-aware context for auditable multi-agents AI systems. So this work was produced by myself and Professor Dr. Cláudio Gayer from the Federal University of Rio Grande do Sul, and it has been published in the International Conference on Artificial Intelligence in Society. So to start, I'm going to talk about the current state of AI, and artificial intelligence is shifting from task executors to autonomous agents that orchestrate complex workflows in dynamic environments. These systems increasingly make consequential decisions by integrating diverse context inputs. So critical context is frequently encoding prompts, local variables, transient logs, rather than being structurally preserved and queryable. This raises a series of problems. One of them is the context fragmentation, which we define as the partial or complete loss of semantic provenance during multi-agent handoffs. So semantic payloads are not retained, causal chains are not recorded, and temporal sequences are not queryable for audition and debugging. This can produce inconsistent behaviors, difficult debuggability, and renders root cases analysis infeasible. So an example of this problem of context fragmentation in multi-agent chains is presented here, and we have agents A, B, and C. Agent A starts with initial context, which is transformed and hand off to the agent B. Agent B also works on this context and hands it off to agent C. When it arrives at agent C, the context has completely shifted, and we have no way to know the exactly tracking traceability of which agent changed the context, which model this agent was using behind it, because different LLM models can produce different results. Some LLMs can have bias regarding some subjects, and this can be kind of a problem when we talk about high risk domains, which I'm going to explain later. So here the work is PAC-AI is a protocol proposal. And why do propose a protocol and not simply use a logging mechanism? So this problem between this comparison between structural versus logging is not a new one. After a cyber attack to the SolarWinds USA software company, this discussion has been going on for quite a while, and the community find out that simply logging is not enough. For instance, in their deployment pipeline, the company had a functionality that was compromised, and yet the logging remained the same while the binary was completely different. So simply logging is not enough, and the community has realized that in this use case, and the community response was a 3 layers protocol stack. So a protocol is much more robust in these high risk domains that we will discuss later. For instance, the EU AI Act defines some high risk domains that I will talk about them very soon. So here they are, the regulations, the EU AI Act. So this is the standard regulation that we use, but there are others in other countries. There are some countries that are still working on their AI regulations, but here we use as the standard, the base one, the EU AI Act, because it's the most complete, and there is a deadline that's approaching in August this year. So we use the EU AI Act as base to design our protocol, but it can also work with other regulations around the world because they are pretty much the same in some key requirements for high-risk AI. For instance, this kind of regulations define transparency, so users must be informed when AI is in use. Explainability, decisions should be understandable. Human oversight, so the ability to review and override AI decisions. Data quality, risk management, documentation and traceability, so record keeping and auditability, so an auditor must be able to check how a decision was made and if there was some human oversight. And to also another problem is robustness and security. So how can we debug some systems and know exactly which agent has taken some decision and which model it was using? So this is also a problem that PAC-AI can help with. So here are some comparative dimensions for our related works. We have chosen these dimensions due to the EU AI Act and the demands that it produces. And some of them are runtime, which is basically the ability of the related work to perform logging of their tasks, although simply logging is not enough. Provenance, here we use the W3C PROV standard, and this is related to Article 12, traceability of the EU AI Act. Governance, so the ability to perform some governance activities in the pipeline. Risk-based, so the EU AI Act defines some risk-based sectors, for instance, healthcare, education, hiring, loans, financial analysis. So in these cases that there are some decisions that can involve some human lives, the UI defines them as high risk. And the layered semantic is another comparative dimensions, which describes the ability of the related work to describe the situation in a layered semantics way, which helps to query later, and also in real time to find to debug a multi-agent systems and to find out what is happening and which agent is producing certain outputs and why. So these are the 5 comparative dimensions that we have defined, and these are the related works that we compared against. The closest one is PROV agent, but it still is a little bit different. It does not use layered semantics the way we do, and does not take into account in their governance layer the risk based in the way that we do. So the biggest gap that we have found is that no one of these works use layered semantic combines with the standard W3C provenance, which is what our main contribution. So we actually, I will describe this later, but we combine these two lines of work to create PAC-AI. But before, I will describe some principles that are behind the PAC-AI design, which is semantics payload is different from provenance. This was what I just talked about. And it means that the semantics is different from the provenance. And we have standard works on web semantics, and we have standard works on provenance. And in PAC-AI, we combine the best approach in our view for this context of multi-agent handoff from each of those areas. So the second principle is the protocol envelope, the ontology, the protocol envelope, and ontology as payload. So they are not bind. So we have the envelope and the ontology can be an external ontology. So we can use PAC-AI to describe any kind of domain. So in any domain we can use PAC-AI because the ontology and the context domain is not binded to the protocol itself, to the envelope itself. It's external to it. It's domain agnostic. So the third principle is record the artifact actually used. So an agent or a pipeline of agents can produce different and many kinds of artifacts, and the protocol makes sure that the actually used artifacts are recorded. So these are the three principles that we build on, and these are the main lines of work that I have just described that we combine to. So we have on the left side here the semantic web via user modeling, and in this line of work we have a well-established, in our view, work which is UserML from Heckman. And this work structures semantic context for UbiComp via layered situational statements that answer what, but not how it was derived. Actually, it does answer a little bit of how, but not in the way that is needed for multi-agent systems. So we use this work from Heckman, which is UserML, to describe a context. But we complement it with the standard web provenance W3C PROV that formalizes causability via entity activity agent graphs, which capture execution level provenance but not the semantic lifecycle. So these both works complement each other and they are the best in their fields. So that's why we combine them. But of course, the protocol has many more attributes to specify governance and other things that are important for multi-agent systems that go beyond these two works. But they are the main core differentiation from our work to the related works. So by doing this, by combining these two lines of works, we solve one of the biggest problems of EU AI Act, which is explainability during real time. When the system is running, we can query to see how it is working, to debug it, and to show for instance, a job candidate which of his information is being used to make a certain decision or not. Depending on the domain, we can use it in a different way. For instance, in the health domain, we can use it to query to see which of the information is being used to classify a triage emergency state, for instance. So I will show more about the domains later. And this also allows, combining these two works, also allows us to query in real time and also to query later for post-hoc rationalization. So the envelope of the protocol is divided into three layers, which are the core block, the payload block, and the privacy compliance and proof block. So lifecycle management is layer 1, which is the core block. Layer 2 is semantic context, and layer 3 is provenance governance. So I will talk about each of these layers. So this is the full package of the full envelope, and here are the three layers that I just described. And inside the lifecycle management layer, which is the core layer, we have context ID. We also have schema version, producer, created at, time to live, status, scope. And this is the core attributes, and we have their descriptions here. You can read it with time. They are well described in the paper too. And in the layer context, in the semantic context layer, we have the payload, which is semantic payload, which is a UserML situation report. UserML situation report is a set of situation statements which can contain observation, interpretation, situation, and application. And by the side here, I also put the article from EU AI Act that this helps to answer. The artifacts registry, the passed artifact pointer, the decision influence, and in the provenance and governance layer, we have some different blocks which are privacy, compliance, provenance, and proof. So privacy are attributes related to privacy of this envelope. Compliance have different attributes. The risk level, we can have high, medium, low. Depending on the risk level, we can have different forward policy. So for the forwarding policy, I will also describe later, and they help to make sure that a pipeline of AI agents does not use raw data but only semantic data. So if the forward policy is defined as semantic forward, we cannot have raw data. So in this way, we can create different pipelines. For example, a pipeline that is raw forward that allows to capture raw signal, and process them into an ontology. And after we have this ontology in a semantic way defined, we can forward this handoff to a pipeline that is only semantic forward. So in this way, the decisions are made in that pipeline using the semantic data and not the raw data. For instance, we can have an essay that a student has produced, and in some cases, depending on the word choices, the writing style, the LLM can know that student is from a certain country and have bias toward the grades. So we can create two pipelines here. One pipeline that extracts the rubric, what is being analyzed, the main ideas, the punctuation, the criteria of evaluation of that text. So we can have a raw forward pipeline that extracts all those into a semantic payload and forward that semantic payload to a pipeline that's only semantic forward. So this is what the compliance helps and the risk level helps. We also have human oversights required here, which can flag that output is required to be seen by a human before it goes on the pipeline. The model card half, which describes the exactly LLM model that was used in this case, because different LLMs can produce different results. Some can have bias toward a certain writing style, others not. So an agent can use one time one model, another time another model. So it's important to be sure which model exactly, which version, and all information that we can know about that model should be recorded in each handoff. So we also have the provenance ref, which is a reference to the exactly graph of the state of the multi-agent systems at that time of that handoff, and the signature of the envelope. So we can sign the envelope too and anchor it to blockchain to make sure that that envelope has not been... later we can, for instance, use it actually we can also use it in a scenario when some user may context that may say that that was not exactly envelope that was used, but we can, as we have the signature and we can anchor it to blockchain, we can verify that that was exactly the exactly information that was produced and was used. So the proof helps with that. So I will explain a little bit more about each of the layers of the second and the third layer. The first one is quite intuitive because are just core attributes, but the second layer, which is the semantic context, which use the work of Heckman to describe a context. Here we have a semantic context carry a semantic payload, a UserML situation report. So a report is being shown here. We have inside this report many statements, and each statement contains different categories. So we have a main part, which describes what has happened, the subject, who, what, the auxiliary, what has been done, the predicate, the range, and the object, which can refer to external ontologies, and an administration group. I will explain later in the example. I will show them fulfilled so it's easier to understand. So the main part has all these attributes, and each of the attributes describe, for instance, a different thing. For the subject, the auxiliary, the predicate, the range, and the object can bind to external ontologies, but can also have raw data. For instance, subject can be a man, auxiliary has property, has interest, has motion, has different kinds of, you can have different kinds of auxiliary. The predicate can be walking, so has property, has interest, has motion, walking, or sleeping, and the range can be slow, fast, medium. So a user has a property of being walking, and the range is medium, low, and fast, and the object is fast. So when we define in this way, the semantics is much easier later to query it and debug exactly what is happening, which agent has classified in that way. And this is just a short example that I have described, but here we have a more concrete one that is used in one of your use cases. So we use the semantic payload here to describe a user, a patient in a healthcare scenario, which has a main part, which is subject, patient 42, has auxiliary, has finding. The predicate is a clinical finding. The range is a reference to an ontology with different clinical findings listed, and the object is the exactly clinical finding object that patient is related to. The explanation, we have also a group inside this statement that's named explanation. It has a confidence. We here have the creator, the agent ID that made that classification based on some raw input that it received, and the administration that show that this statement belongs to the group of interpretation. So here is a more concrete example on how the semantic payload can be fulfilled, and using this structure we can have the debuggability and traceability in real time and also afterwards. So we know exactly that the semantic payload will always have a main part with a subject, with auxiliary, with a predicate, with a range, and an object. And depending on the domain, they will be fulfilled different. And also we can have different attributes here. In this case, we have the explanation because this is an interpretation group. So this is what I just described, how the semantic layer works briefly, which is the second layer, and now I will describe how the third layer works, which contains the provenance. So the provenance is the full graph of the multi-agent systems at the moment of a handoff. So they are external to the protocol, and they are linked in the protocol via an attribute inside the protocol. So after each handoff, the full graph is linked inside the envelope that shows the state of that multi-agent systems at that handoff, and which agent was associated with which task, and that task produced which information, which payload. So in this way, you can also be sure that which was the agent and how its decision was arrived. So here we have the full example of one of your use case envelopes with all informations fulfilled. We have the semantic payload that I just showed. The core attributes are listed here. And here below we have the governance data, the artifact registry, the forwarding policy that I described in the beginning. In this case, is semantic forward, because I have extract the semantic context, so the forward policy is semantics. And the password artifacts, the proof, and the provenance half. So this refers to external provenance graph of the current state of the multi-agent system at the time that this semantic extraction was made. So we can be sure which was the exactly state, and the agent and the task, and the LLM behind that agent that produced it. So the governance layer, which is the third layer, has a risk-based compliance, which in this case we recommend that for low risk scenarios we can have raw forwarding, but to medium to high it's more recommended that we have semantic forward, because those scenarios of high risk in the EU AI Act they mandate that we have full explainability and traceability, for instance, healthcare, education, and so forward. So in this case, we may need to have the full traceability. We recommend choose semantic forward. So I have described already how the semantic forward works, but we have here another example that shows that. And when we have this agent that produce a semantic payload for a following agent or pipeline of agents to produce decisions on top of it, we have a reduced attack surface because we know exactly the semantics that those decisions are being made on. So if you have the raw data, for instance, the ESI of the student, we cannot be sure that those evaluations are not biased or not, because they may use the writing style. But as we have extract the semantics with the main idea, the punctuation, what we are evaluating, we can be sure that the bias is in this case is reduced. So this aligns with audition, helps with the debuggability. And in the case of the raw forward mechanism, the vectors or the tokens, we can forward the exactly outputs of an agent to another, and this may difficult debuggability, auditability, and bring some other problems. It's recommended for low risk scenarios. So the reference implementation, we have implemented Python SDK, which is open source and is available. And we are signing each envelope under 4 milliseconds using the standard JSON canonization. And we also have produced some audition verifiers that help exactly to answer some of the EU AI Act questions. For instance, the temporal oversight, as we have the provenance graph, the full data of the semantics too, we produce this verified temporal oversight to know if a decision had human oversighted and how long it took for this human to make a decision. This eliminates rub stamping. For instance, we also have the verify negative proof that help to show that data was not used. Verify workflow isolation that shows the raw forward and the semantic forwards pipelines were isolated, no data was used between them. Verify integrity, that we can see that the envelope is correctly signed, and verify personal information detachment. So in this case, we have personally identifiable information detachment mechanism that aims to reconcile the audit traceability with the rights to erasure. So the EU AI Act have this question that requires for us to be able to have auditability, traceability, but another laws mandate the right to erasure. So what we do, we have PII detachment mechanisms that converts the private information to tokens and isolates it in a vault, the private informations and that token. So if the user wants to be forgotten, we can just delete it from the vault, but we also have the traceability in an anonymized way. So this is how we reconcile these two conflicting laws. So more information on the tests, we are signing the envelopes using the standard JSON canonization under 4 milliseconds in a commodity hardware, and using more sophisticated canonization takes a little bit longer. This is recommended for multi-principal scenarios, for instance, and this is the time that it takes to query the provenance graph with approximately 500 entities. So the evaluation scenarios, we have a financial scenario that uses the 4 verifiers that we produced, and it helps to see that gender, ethnicity, marital status were not used in the decision of the loan. We also can see that a human has oversight the decision to allow or not that loan, and the workflow isolation to see that the forward and the semantics were not related, and the pipeline detachment, the informations of the text ID, account number are not being used by the AI and are not inside the LLM. So in the case here, these are complementary information that are not exactly in the paper, but I will describe about a health case scenario with 2 pipelines, raw forward and a semantic forward, and we have a signal, the raw signal data, and which is used by another agent that classifies into an ontology. They both related to Web3 provenance graph at each at the handoff, and then they produce a semantic payload that feeds in another pipeline, which is semantic forward. In this case, the semantic data is used to make the triage, allocation, and the clinical oversight. They are all connected to Web3 provenance, and they can all be checked with the verifiers that we have developed in the SDK. So this is another evaluation scenario, which is the education scenario. We have 2 pipelines here too. One is raw forward that extract the exactly information that are being evaluated in a text and feeds into a second pipeline, so we can evaluate the text without the possibility to be biased toward the writing style of a certain candidate ethnicity. So here we have the exactly article that they are connected. Each of these stage helps of the UI Act, and the verifiers how they are used to. So These are the different scenarios that we use to evaluate our protocol. We have developed them with PAC-AI, and they are available in our GitHub repository, which I will show later. So, some description about the attack vectors that can have in this kind of systems. Each artifact misreporting, but we solve that with hash and blockchain anchoring. The provenance graph forgery also, so we sign the provenance graph. And the envelope replay attack, but we have a timestamp and a immutable pointer that we can be sure which are the sequence of artifacts should be like. So our key contribution is a 3-layer protocol that separates semantics from provenance and allows different kind of mechanisms that we have created called the semantics and raw-forward that can show exactly at what agent a decision was made, or what agent analysis from raw to semantics was made to. So the protocol used two well-established lines of work from web semantics and web provenance and integrate them into its envelope. And it has also a risk-based configuration model, and it's aimed to be compliant with the EU AI Act, but it also in future works we plan to see other regulations world around and how they are connected, although we have already checked some of them and see that they are mostly the same in the problems that we are talking about of explainability at least. So we also aim to evaluate our protocol in a real case scenario since our use case was simulated from now on. So this is all. Thank you very much. These are the reference lists that you can go and see for yourself, and this is our GitHub repository. Thank you very much, and this has been PAC-AI and how it aims to solve this problem of multi-agents handoffs in AI systems. Thank you.